Greetings, everyone, and welcome back to a new lecture. We're looking at section 1.3. So, here's some terms I want you to become familiar with. One, solution curve. Two, slope field, isoclines, and the equilibrium solution. Okay, so first order differential equations have a nice geometric interpretation, since dy dx can be interpreted as the slope. Okay, a solution curve is the graph of the solution to a differential equation. So let's look at something basic. Okay, if we wanted to find the general solution to y prime equals 3x, how would you do it? Well, start here. Y prime equals 3x, a nice first order differential equation. Okay, to find out the family of solutions that solve this differential equation, all you do is integrate both sides. You get y equals, 3 halves x squared plus c. Okay. After choosing a value for c, we can plot the resulting curve. Okay, so I'm going to do this, but I'm only going to do this for a handful of functions. So we can look at what happens when c is equal to 0, when c equals 1, and when c is equal to 2. Okay, now c can be a lot of different things, but bear with me on that. What does 3 halves x squared plus c looks like? Well, it's a parabola. Okay, and what does 3 halves x squared plus 1 look like? Well, it looks like that. And plus 2 will look like that. Okay. Now, this is just an example I'm using to illustrate a point. And this is the point that I'm getting at, is the next step. What is the slope at any given point on the solution curves? Okay, so if I look at right here, what is the slope of the tangent line? What's y prime? Well, it's 0. What's the slope right here? It's 0. What's the slope here? It's 0. Now, why is it all 0? It's because the differential equation says it's 0. Because the x-coordinate of all these values is 0. The y-coordinate is different, but the x-coordinate is 0. And the differential equation says take your x-coordinate and multiply it by 3, and that's the slope of the solution curve at that point. So because x is 0, y prime is 0 at all of these. If I made x 1, okay, so let's estimate where like 1 would be. I don't know. Let's go to about right here. Okay, what's the slope here? It's 3. What's the slope here? It's 3. What's the slope here? It's 3. Okay, right here, negative 1, it would be negative 3. Negative 3, negative 3. Okay, so this is something that each one of the solution curves has in common. The slope at any particular x on any solution curve will be the same. Now, that's only because the differential equation involved x and not both x and y. Okay, so this is special to this case. But it gives us an important task or important idea to flesh out. Okay, we can use the slope interpretation in cases where we don't have the solution curve. Okay, some differential equations are not going to be this easy. In fact, most aren't. There are going to be some differential equations that are going to be really, really hard to solve, or some that are impossible to solve. Like not every integral has an antiderivative, okay, or closed form antiderivative, I should say. So in those cases, we can approximate a solution by looking at what's called a slope field. Okay, so a slope field is a sketch of many short straight line segments showing the slope of the differential equation, of the solution to a differential equation. Okay, so let me turn this page upside down. Sketch the slope field for y prime equals negative x over y, and use the slope to draw some approximate solution curves. Okay, so this is a really boring labor. Well, it doesn't involve a lot of labor. You'll see why we'll do it once and we won't ever do it again. Okay, but let's take a look at it. Okay, So we have the differential equation, y prime equals negative x over y. Okay, and let's look at some different values of x and some different values of y. Okay, so let's go, x over here, and let's let y be right here. Okay, and these aren't axes, I'm going to generate a table, so I don't want to confuse you. Okay, so let's let x be -2, -1, 0, 1, and 2. And let's let y be what? -2, -1, 0, 1, and 2. Okay, so there's our grid. Okay, so at the point, so the green color is representing a particular location on the curve. The red color is representing an actual slope, the y prime value. So if x is -2 and y is -2, okay, then we have a -2 over -2. So the slope is -1. Okay, so all again, I'm just plugging in x and y into this differential equation. Okay, what happens if x is -1? Okay, so that's 1 over -2, so that's -1/2. If x is 0, that's 0. If x is 1, I get -1 over -2, that's +1/2. And if x is 2, I get -2 over -2, that's going to be what? 1. Okay, and then we go to the next line down. Let x be -2, let y be -1. So -2 times negative is 2, divided by -1, that's -2. And we keep playing the game. So you can see why I'm not really thrilled with this. That's -1. If x is 0, then y prime is 0. If x is 1, now we're at -1 over -1, so that's 1. If x is 2, it's -2 over -1. That is 2. If y is ever 0, then this doesn't exist, okay, because you can't divide by 0. So let's get rid of that. And keep going through this. If x is -2, now I have a -2. That's +2 divided by 1, that's 2. That's 1 divided by 1, that's 1. That's still 0. That's 1 over 1 is 1. And 2 over, -2 over 1 is a -2. And lastly, if x is -2, that's 2. 2 divided by 2 is 1. This will be what? 1/2. This will be 0. This will be -1/2. And this will be -2. Sorry, 1. Okay. So I did all of that so I could sketch the slope field. So the slope field for y prime equals -x over y. And I'll go to each of these ordered pairs. Okay. At 0, 0, well, there is no slope, it's undefined. Okay. What about when x is 0 and y is 1? Well, the slope is 0. What about when x is 0 and y is 2? Slope is 0. Same thing down here. Next, when x is 1. So when x is 1 and y is 0, that's nothing. When x is 1, y is 1, the slope is 1. So this is the first interesting one. That, to me, at the point 1, 1, looks like a slope of 1. When x is 1 and y is 2, sorry, this is a -1/2. Okay, well, that makes this wrong. All right, so that's a -1. All right. When x is 1 and y is 2, the slope is -1/2. So we're looking at something that's a little bit flatter. Okay, so that's a slope of -1, it's steeper. That's a slope of -1/2, that's flatter. What happens when y is -1? The slope is +1, so there's that. And when y is -2, the slope is +1/2. So that would look like this. Okay, and we keep playing this game. So now x is 2, and we'll just work from bottom to top. So at x equals 1, x equals 2, 2, negative 2. The slope is 1. At 2, negative 1, the slope is 2. So that's the steepest one we've seen so far. Okay, when the slope is, when x is 2 and y is 1, what do we have here? Negative 2. So now I'm down like this, and then I'm down like that. Okay. All right. And we do the back half of this. Negative 1/2, negative 2, or sorry, negative 1, negative 2 is the slope of negative 1/2. So that's that. Slope of negative 1, that's that. Slope of positive 1, that's that. Slope of 1/2, that's that. And the last group, negative 1, oh, that's negative 1. Then negative 2 is steeper, positive 2 is steeper, positive 1 is flatter. Okay. And so what we do here when we draw a solution curve, okay, so now we're looking at an initial value problem. An initial value problem requires a differential equation, which is right here, and an initial condition. So what would it look like if you had a solution that passed through the point 0, 2? So that's this point that's right here. Well, it would be flat for a while, and then it would pick up this downward trajectory, and it may look something like that. Okay, but you have to consider what happens in the back half. This side, it's increasing, so it looks something like that. So what does that look like? Well, to me, it looks like a circle. Okay, what happens if you're looking at an initial condition? So this is, the blue curve is for the initial condition that y of 0 is 2. What happens if I had an initial condition of y of 0 is negative 1? Well, that means I'm going through this point that's right there. So that's flat, and then it goes up, so it look like that. On the back side, it would look like this. Instead of playing connect the dots, really what I'm doing is playing connect the arrows, okay, because that's what's going on here. And in both cases, it looks like I'm sketching something out that looks circular, okay? It can be shown, and we will show it eventually, that the solution to this differential equation, the general solution, is circles of different radii. Okay, so we're not going to show it in this lesson. We have to wait another lesson or two to get there, but that's what we've just traced out. Okay, so at this point I'd ask if you had questions, but hopefully you don't, and you kind of get the gist of what we're doing. We're plugging in a bunch of x and y's into our differential equation. Whatever the output of that is, that's the slope, the little short line segment, the slant of the little short line segment we plot at that ordered pair. And then given an initial condition like y of 0 is 2 or y of 0 is negative 1, we start there and we just play connect the arrows. Okay. All right. Next. For a differential equation of the form y prime equals f of x comma y, okay, so this is the form of the differential equation above, okay? So there's an x input and a y input. An isocline is defined to be a curve f of x, y equals k, where all solutions passing through a given isocline have a slope of k. Okay, so what you do, you think of that. Okay, there were, let me get a new sheet of paper. There were certain ordered pairs in the differential equation above, negative x over y, where which had a slope of 0. Okay, which ones were they? Well, you'd set y prime equal to 0, and you'd say negative x over y, multiply over, you get x is equal to 0. So, along the line x equals 0, you had a slope of 0. So right there, right, oh, we didn't count that one, there. Okay, there are some which had a slope of 1. Okay, so you'd set y prime equal to 1, and you get negative x over y. This one will be more interesting. Cross multiply, you get the function y equals negative x. So if I looked right here along the line y equals negative x, what was the slope at negative 2 comma 2? It was 1. What was the slope at negative 1, 1? It was 1. Forget about that one, I understand. At negative 1, the slope was 1. At 2, negative 2, the slope was 1. So what you see here is that along certain lines or curves, okay, in this case it was a straight line segment, the slope was always going to be a given value, in this case 1. And you could do this for if it had a slope of 2. Okay, negative x over y, you get y equals negative 1/2 x when you cross multiply. So if you look at y equals negative 1/2 x, okay, right here, right there, sorry, negative, it'd be right here and here, there was slopes of 2. So that's what an isocline is. The isocline that we're most familiar with is the one that we use for x equals 0. I should give you a little bit of a heads up. As you can tell, I really don't like the curve sketching process of this, where you have to, take the time to find out what a slope is at any given point, plot it on a graph, hope that what you're plotting on the graph is truly representative of a slope 1 or 2 or 1/2 or negative 1/2, and then play connect the dots. Technology is so much better at it than we are. So what I would do, instead of making you sketch everything out, is give you a slope field that's computer generated and have you match it up with the appropriate differential equation. So it would be more like, I give you a pretty picture of this with lots of arrows, and I say, which one of the following differential equations is this the slope field for? So that's just a little heads up. Or I would say, given this slope field, find the particular solution that passes through 0, 2. And so you'd put your pen right here, and then you'd say, all right, well, connect the arrows. It looks like that one. Okay, so I just wanted to have a little disclaimer on that. Sketch the slope field for, here we go again, y prime equals y times y minus 1. Okay, that's much more complicated than this one right here, but I can give you little tips on how to do it a little bit more quickly. And then I want you to draw the solution curve through the point 2, 1. And what is the special about y equals 1? All right, here we go. So the differential equation, y prime equals y times y minus 1. Well, the first thing that you notice is that this doesn't involve x, it only involves y. Okay, so that will make our process a little bit faster. If I tried y equals 0 into our differential equation, okay, if y equals 0, what's y prime? So we'll do this. This is my input y. I don't have to worry about x because there is no x's in this differential equation. So if I plug in 0 for y, what is y prime? Well, if I plug in 0, it's 0. So at any point with y coordinate 0, you will have a slope of 0. That's neat. What about 1? At y equals 1, we have y prime equals 1 times 1 minus 1. It has a slope of 0. And again, that's independent of x because x doesn't play a role in the differential equation. What about when y is 2? Okay, if y is 2, then this is 2 times 2 minus 1, so that's 2. So the slope is always 2 when y is 2. Slope 2 at every x value okay, and let's pick one more. Let's pick some value between 0 and 1, like 1/2. So if this is 1/2, 1/2 minus 1 is negative 1/2 times 1/2 is negative 1/4. So at 1/2, we have a tiny slope of negative 1/4. If I had picked 3/4, this would be negative 1/4, this would be 3/4. I would still have a negative slope. Okay, it would actually be a little flatter. It'd be just slightly negative. Okay, and if I had picked 1/4, I would have a negative slope. Again, that's slightly more flat than the negative 1/2. Okay, so that's what the slope field would look like. I could do the same thing for the bottom, but you know, at the risk of boring you to tears, I don't want to do that. Draw the solution curve through the point 2, 1. So where's 2, 1? So that's y equals 2. That's 1, 2. That's y equals 1. So what does the solution curve look like? I'll draw it in red. It looks like this. We have a flat slope here. So we go to play connect the dots. Well, if they're all flat slopes, then I have a horizontal line. So this is the thing that I just drew in red is the solution of the differential equation y prime equals y times y minus 1 that passes through the point 2, 1. So what is special about the value y equals 1? Well, no matter what ordered pair, it doesn't have to be 2, 1. It could be 1, 1, negative 1, 1, negative 2, 1. I'm going to generate a horizontal line that is the solution curve for our differential equation. Okay, is there anything else that's like that? Sure, the origin. Not the origin, the x-axis. Okay, there's another horizontal line where any initial condition, any point that starts on this line stays on this line forever. Because you can see what would happen here at the point 0, 1/2. You would have a solution curve that looked like that. Sort of like a little ski slope right here. So there's something special about 0 and 1 for this differential equation. So here's the definition. Differential equation of the form y prime equals f of x comma y, like the one is that we're looking at, even though x is not in it, it's still of that form. If y equals y naught, where y is the dependent variable, makes y prime equals 0, then y equals y naught is an equilibrium solution to the differential equation. Okay, so this is a definition that's relevant to us. An equilibrium solution. So if there's a particular value of y that makes the differential equation equal to 0 always, then the differential equation is, then that y value is the equilibrium solution. So, quick little example. Find all equilibria to the differential equations. Okay, so y prime equals x squared y. Can you think of any value of y that makes y prime equal to 0 and always 0 regardless of what x is? Well, yes. Y equals 0 is an equilibrium solution. Okay, just as a flashback to yesterday's lecture, is this differential equation first order or second order? Well, it's first order. It has one derivative of y. Is it linear or nonlinear? Okay, well, y prime is a linear term. X squared, that's a constant relative to y, so this is a constant times y, that's a linear term. And what was the last one? It was homogeneous or non-homogeneous. Well, if y equals 0 is a solution to the differential equation, we said that was a homogeneous differential equation. So this is a homogeneous differential equation. Okay, what about b? Y prime equals 2x times y squared minus 9 over x minus 3. Again, we're looking for values of y, not x, y, that make the differential equation equal to 0, or y prime equal to 0. So that's y equals plus 3 and minus 3. Okay, and we don't care that x equals 0 does, and we don't care that x equals 3 causes division by 0. We only care that 3 and negative 3 are the values of y that makes y prime 0. Okay. Lastly, y prime equals x over y. Okay, in this case, there's no value of y that makes y prime equal to 0. So there are no equilibrium solutions to that differential equation. All right, so hopefully you're following along. Number 5 is the last example we're going to look at. Okay, solve the initial value problem. Y prime equals 2x times y squared minus 9 divided by x minus 3. That's throwback to example 4b. That passes through the point y of 0 equals 3. Now, all the differential equations that we've looked at up to this point have been very simple, and basically we just used integration to solve the DE. In this case, it's much more complex. So it's not a basic integral, and you could try separation of variables, even though we haven't discussed it in this class yet because you looked at it in Calc 2. But you don't even have to. The hint says look before you leap. Okay? It's this differential equation through the point 0, 3. Well, we just got done talking about equilibrium solutions. Okay, where were the equilibria of 4b? Well, positive 3 and negative 3. And we want an initial value, particular solution that passes through the point 0, 3, or 2, 0, 3. So because 3 is an equilibrium solution, and because the initial condition goes through y equals 0, 3, then we know what the graph is. I don't even have to sketch all those little arrows. At the point 0, 3, because it's an equilibrium solution, the solution curve is flat. All right, so that is section 1.3. Okay, so if you have any questions, please feel free to go to office hours or the Zoom link for office hours. I'll be happy to help you. Take care and have a great night.